All right, so a rule of inference, like the ones we just talked about, hypothetical syllogism, modus ponens, modus tollens, etc., these are all valid argument forms. A rule of equivalence is different because it's a pair of logically equivalent proposition forms. So a pair of propositions is semantically defined as logically equivalent when they have the same truth values in every row of their truth tables. So we talked about this before. So in the book that we're using, the metalogical symbol with these sort of two arrows will be used to indicate is logically equivalent to. Uh, that's just something to flag going forward. So we'll go ahead and start here. The first rule of equivalence is De Morgan's law. Um, this is an incredibly important and incredibly useful one to remember. A lot of the time, when you're kind of stuck on a proof, you're not sure what to do, De Morgan's law is likely to be something that gives you an answer. So, De Morgan's law there are two ways that it does the same thing, but obviously because one of these well-formed formulas is logically equivalent to the other, they can be swapped in both directions. Sort of. There, there's some stuff to keep in mind here. But so first we can see that one example is if we have the formula, it's not the case that A and B. This is logically equivalent to. Sorry, it's not the case that alpha and beta is logically equivalent to not alpha or not beta. So let's think about what this means. If I in the first formula it says it's not the case that A and B. So I know that if A and or again, it's not the case that alpha and beta. So if it's not the case that alpha and beta, then alpha and beta can't be true. At least one of them is false. Maybe both of them are false. Uh, so either alpha is false or beta is false, or alpha and beta are false individually. So we have three options. So we can see that this is logically equivalent to if I said, well, either not alpha is true or not beta is true. And because we have an inclusive disjunction here, it's also possible that neither alpha nor beta are true. But because the first formula, it's not the case that alpha and beta, it's just saying, well, we don't have both alpha and beta. So I know that it's either not the case that alpha or it's not the case that beta because we can't have both. All right, so that's one version of De Morgan's. Now the second version of De Morgan's. So something I'll flag in the first place. It's very important to pay attention to when you're moving from one thing to another with De Morgan's. The operator changes from a conditional to a disjunction. Uh, so in the first case, it's not the case that alpha and beta. The major operator here is a negation. And the major operator in the second case, it's not the case that alpha or it's not the case that beta. The major operator is a disjunction. But the thing in the middle is that it moves from being a situation where with a conjunction that is entirely negated to a disjunction with each of the disjuncts being negated. Very important to remember that it moves from a conjunction to a disjunction. And in the second case, which we're about to talk about, it moves from a disjunction to a conjunction. Any application of De Morgan's does not maintain a conjunction to a disjunction or a disjunction to a conjunction. Very important to remember. That's an easy mistake for students to make. So the second example is it's not the case that alpha or beta, and so because this is an inclusive disjunction, this means that, well, if it's not the case that alpha or beta, then this means that we have neither alpha nor beta. It can't be either one and it can't be both of them. So we can express this also as it's not the case that alpha and it's not the case that beta. So from it's not the case that alpha or beta, we can get to it's not the case that alpha, and it's not the case that beta. This one is especially useful in um, proofs because you'll often run into situations where you'll have a bunch of stuff inside of a disjunction that you wish you could pull apart. And if you can find a way to negate that disjunction, well, then you can apply De Morgan's and turn that disjunction into a conjunction. And once it's a conjunction, then you can pull apart each of the individual elements using simplification. Disjunctions you can't do that with. If it's just a disjunction, we can't pull apart any of the individual elements because we're not certain about which ones are true. But if we can get things into a form like this, where it ends up being a conjunction instead of a disjunction, then we're able to simplify out parts of it that we might want to work with. So that's going to be the main way in which De Morgan's is useful. All right, so here's just an example of how rules of equivalence are going to work. If you're suspicious about any of these, you can go ahead and plug them into a truth table, and you'll see that it turns out these are going to be logically equivalent. So we have our base columns here, S and P. We have our first statement. It's not the case that S or P. So the major operator is this negation. In the second case, it's not the case that S and it's not the case that P. The major operator is this conjunction. So we can see that in both of these columns, the truth values are false, 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 true. So these are logically equivalent, but hopefully De Morgan's is, I think, relatively easy to wrap your head around in terms of understanding why, if it's not the case that S or P, then this means that it's not the case that S and it's not the case that P. Okay. So rules of equivalence can be used in both directions. So they can apply, because it's equivalent, we can go either from it's not the case that alpha and beta to it's not the case that alpha or it's not the case that beta, or vice versa. We can go from it's not the case that alpha or it's not the case that beta to it's not the case that alpha and beta. They're equivalent, so they move back and forth. Rules of inference, on the other hand, can only be used in one direction, from premise to conclusion, not back again. Although, if you're correctly moving from premises to conclusions, you shouldn't need to go back because whatever premises you use to get to some conclusion in the first place is going to still be there in your proof in an earlier line. So you could use that line to reference it if you needed it for some reason. So rules of, again, this square thing is coming up, but the square here should be a vel. I don't know why some of my vels aren't showing up. But rules of equivalence apply to any part of a proof, not just whole lines. So because rules of equivalence is just a different well-formed formula that you can drop in place of another well-formed formula, it's possible to apply it to just one section of a larger line. So we can see here in line 1, we have a well-formed formula where the major operator is the conditional. If it's not the case that A and B, then it's not the case that P. But we can apply De Morgan's to line 1 and get, in the second case, it's not the case that A, or it's not the case, if it's not the case that A, or it's not the case that B, then it's not the case that P. One thing to pay attention to is where the parentheses are here. Because the major operator in the antecedent of the conditional in line 1 is the negation, and it's applying to this conditional of A and B, and we're changing this entire thing to a disjunction between not A and not B, we need to make sure that we put parentheses around the entire thing to show that it is this entire formula that is the antecedent of this conditional and maintain that it's a well-formed formula. Very important to remember what to do with the parentheses there. All right. So next is association. So this is one of those rules that you might find sort of annoying and obvious, but you're going to have to take your time with. So if we have a formula like alpha or beta or gamma, well, we can use a line to move the parentheses from one part of this formula to another, because really this is just a string of or statements. And where the parentheses are here doesn't really matter, but we do need them somewhere, because otherwise things get messy. We wouldn't have well-formed formulas anymore. So we can have alpha or beta or gamma, or we can have alpha or beta or gamma. But we need to apply a rule in order to move those parentheses around. Now this also applies for conjunctions. If we have alpha and beta and gamma, this is the same as saying alpha and beta and gamma. Because in this case, well, we have alpha, we have beta, we have gamma, and we're just grouping them together in different ways to say that we have all of these things together. But they do need to be grouped. They do need to stay in parentheses so that only two things are ever connected with a conjunction at one time in order to be a well-formed formula. So association allows us to regroup the propositions when both operators, when they share a conjunction or a disjunction as their operator. Now this is important because, well, most useful, maybe not most useful, but commonly useful when, let's say, if we started with the formula alpha and beta and gamma, and we wanted gamma on a line by itself, well, first we would have to apply association, and then we would get alpha and beta in parentheses and gamma, and then we could use simplification to get gamma by itself. We wouldn't be able to use simplification on gamma while it was locked inside the parentheses with beta there. So we would need to move the parentheses over to alpha and beta, and then once gamma is hanging outside, once the major operator is between gamma and alpha and beta, then we can get gamma on its own using simplification. All right, so careful. Association cannot be used when the operators are mixed. If we have S or A and B, we can't use association to move the parentheses over. We can only use association when we have all disjunctions or all conjunctions. So that's very important to keep in mind. Association cannot be used on any operators other than conjunction and disjunction. So, well, conditionals are especially obvious, but if we have if S, then A and B, well, we can't just move over to if S, then A and B. It's not a correct application of association. Okay, next is distribution. So this is a way to manipulate situations in which we have a combination of disjunctions and conjunctions. So if we start with the formula alpha and beta or gamma, well, we can get to, in parentheses, alpha and beta or alpha and gamma. We know that we have alpha and either beta or gamma. We don't know which one. So we could also express this as, well, we have alpha and beta or gamma, or either we have alpha and beta, or we have alpha and gamma. We know that one of these two things is true. We don't know which one is true, but we know that one of them is true. Now, conversely, if we have a different well-formed formula that says alpha or beta and gamma, we know that either alpha is true or beta and gamma is true. Then we can change this to either alpha or beta and alpha or gamma. So one thing that's really important with these is to keep in mind where the conjunctions and where the disjunctions go, and where they have to be swapped. It can be real easy to mix up where you're putting your conjunctions and your disjunctions, so be really careful with that. All right. Next, commutativity. This is one that's super annoying for everyone, because a lot of the times it's just extra steps that it feels like extra steps that you have to do in your proof. But that's just the way things are. So commutativity is because disjunctions and conjunctions, the order doesn't really matter which order they're in. We can swap them back and forth. So if we have either alpha or beta, we can change this to either beta or alpha. That's going to be logically equivalent. And if we have alpha and beta, that's logically equivalent to beta and alpha. So sometimes we're going to have to swap these around. That can be annoying because it just looks really obvious to us that these are equivalent to each other. But it is just a step that we have to apply. Okay, and again, obviously this doesn't apply to conditionals. If S then P and if P then S are not logically equivalent to one another. Here's a truth table if you don't believe me, but it should be obvious with how much we've talked about situations in which conditionals can be true or false, and what we can do with an antecedent and consequent, what they apply about each other, that you can't just swap these around. All right. Next rule of equivalence is double negation. This one's also pretty obvious and might get annoying in some instances, where let's say there's 8 tildes on something and you'd want to use double negation to get rid of all 8 at once. We're going to want to just apply one rule at a time. So double negation allows us to say that alpha is equivalent to not alpha. Pretty straightforward. If it's not the case that it's not the case that alpha, this is identical to alpha. So you can swap these back and forth. This is useful when sometimes we'll need to add negations to things in order to be able to apply certain rules of inference or rules of equivalence. Now you can't just add a single negation to something because that changes the meaning entirely, but you can add 2 negations to something because that keeps the meaning the same. If I have apples, it's not the same as not having apples, but not having apples is in fact the same as having apples. So double negation applies here in both ways. Also, if there's extra tildes on something for some reason and we want to get them off, if there are 2 of them, then we can just apply double negation and get rid of them. Be very careful when applying this to get rid of tildes that you're only ever taking off 2 at a time. You can only take off even numbers of tildes, not odd numbers. If there's an odd number of tildes, then you have a negation. If there's an even number of tildes, you can take them all off and you just have a positive statement. So keep that in mind. All right, next we have contraposition. So the rule of equivalence here is if alpha then beta becomes if not beta, then not alpha. This should make sense because this is kind of just the formal expression of the modus tollens rule of inference that we talked about, where if one of our premises says if alpha then beta, and another premise says not beta, then we conclude not alpha, then that's essentially saying the same thing here, is that if it's true that if alpha then beta, then it's also true that if it's not the case that beta, then it's not the case that alpha. Because we know that if there was an alpha, then there would have to be a beta. So if there's no beta, then we can know that there's no alpha. So contraposition, very important to remember that So we're swapping the antecedent and the consequent on this conditional, and both sides are being negated. One thing to remember is when one of the sides of the conditional in the first place is already negated, you'll have to negate it again if you apply contraposition. Yeah, okay. So when only one formula is negated, you can either add a tilde to both sides or take a tilde off both sides, but you cannot mix and match. So you can see here in the first line we have if not S, then not P. Well, if we apply contraposition, then we get in line 2, if not P, then not S. And then in line 3, we can apply double negation to line 2. But really important to remember step 2. When you apply contraposition, even though not S already had a negation in front of it, you have to add another tilde to it. This will just keep things simple in general. Is even if it looks silly to have a ton of tildes in front of something, always make sure to add the tildes that you need to when applying rules, and then sort of at the end of things you can go back and use double negation to get rid of any extraneous ones. But always add the tildes that you need to. Very important to remember. Okay, next, material implication, which we'll just write as implication when using it as a justification, is a rule of equivalence that allows us to go from a conditional to a disjunction. Now, this one is going to seem a little bit unintuitive, I think. This is one that I would encourage you, if you don't get it, to go ahead and do a truth table for, and you'll see that these are equivalent, but we'll also talk about what they mean. But the truth table is helpful, I think, because the equivalence that's being expressed here is really just the circumstances in which a conditional is true or false, which a truth table reveals. So we start with if alpha then beta, and that's logically equivalent to it's not the case that alpha or beta. Now this seems like a little bit of a leap, but let's think about when it's true that if alpha then beta. It's only going to be false when alpha is true and beta is false. So we have 3 other circumstances. Alpha can be false and beta can be true. Alpha can be false and beta can be false. Or alpha can be true and beta can be true. So if we think about, well, either it's not the case that alpha or it's the case that beta, we can see that the situation in which alpha is true and beta is false from the conditional, or the relation of alpha being true and beta being false is what's excluded here. So either alpha is not true, there's no alpha, and there's a beta, or there is an alpha and there's a beta, or it's both true that it's not the case that alpha and there is a beta, but it's not the case that there is an alpha and no beta. So this one's kind of tricky. Again, I think the truth table helps reveal something about the way this one works, and it's really just about the situations in which alpha and beta are true, given that if alpha, then beta. But this rule is also really helpful because we can see any of these rules that change something from one type of operation to another type of operation, really useful. Especially if we've got some other elements going on. Maybe we have a not beta somewhere in our... Well, if we had a not beta, we could just apply most tolens. It would be simple. But anyway, allowing us to put not alpha and beta from if alpha then beta into a disjunction gives us access to different rules and things that we can use that we'd be restricted from if we left it as a conditional. So this is one that is important to spend some time thinking about. Do a truth table if you have to, if that helps. 'Cause this one's kind of unintuitive, but is important to remember and is useful. All right. Next is material equivalence. So we already talked about this a little bit, and there are some rules that the book has that are specifically for biconditionals. We're not going to do those, and part of the reason why we're not going to get into those is because we have this. Anything that is a biconditional can be expressed in these other ways. And I'm not going to have you do a lot of stuff with biconditionals because it ends up just being a lot of this, but I think that that's worth it for skipping the rules specific to biconditionals, which are extraneous and not really needed. They're mostly for shortcutting stuff, because this will do all the work that we need a biconditional to do. And like the book mentioned, biconditionals in the first place are sort of extraneous logical operators, specifically because they can be expressed in terms of other logical operators. So if we have the biconditional alpha, if and only if beta, this can be expressed as if alpha then beta, and, sorry, this is, give me a second to fix this. Okay. So it's really important that the alpha and betas go both ways with these conditionals, which is why I had to stop and fix this. So material equivalence in the first case, if we start with alpha if and only if beta, this is equivalent to if alpha then beta, and if beta then alpha. It goes both directions. Two conditionals where the antecedents and the consequence are swapped, and there is a conjunction that is connecting them. However, we can also express if alpha then beta as a disjunction between either alpha and beta, or it is not the case that alpha and it is not the case that beta. Now, this one will make sense if you think about it in terms of what the conditions for a biconditional being true are. Either both sides of them are true or both sides of them are false. What a biconditional is expressing is that each side has the same truth value, whether that's true or false. And you can see that the disjunction is a clear expression of that. Either alpha and beta, or not alpha and not beta. Either both of these are true or they're both false. And that's going to be logically equivalent to alpha if and only if beta. Okay. Next, we have exportation. So exportation is a rule of this form. If we have a series of conditionals like this, if alpha, then if beta, then gamma, then we can express this as if alpha and beta, then gamma. So we know that if alpha is true, then it's true that if there's beta, then there's gamma. So if we have alpha and beta, let's say in the first case that if our first premise is just if alpha, then it's true that if beta, then gamma, and we have alpha somewhere and we have beta somewhere, it should be obvious that, well, we have gamma. Because we have alpha, then this relation between beta and gamma holds, and because we have beta, then that shows us that gamma is true. So we can express this as, well, if it's true that alpha and beta, then it is true that gamma. Alpha gives us the material that shows the relation between beta and gamma, and the relation between beta and gamma shows us that if beta is present, then gamma is present. So we know that if there is alpha and there is beta, then we have gamma for exportation. So you can see that this will be useful in different ways. We're able to move the parentheses around and we're changing the operators a bit. In this case, we're not changing the operators in such a way that we'd be allowed to simplify anything out of it immediately. We would have to do some other work first before we could use simplification to just get part of the conjunction. But going from two conditionals to one and moving the parentheses around can be useful in different ways. Okay, so this is something to be careful about. The formulas if S then if P then Q and if S then P then Q are not logically equivalent. So it's not a matter of just moving parentheses around. Remember, we can do that with disjunctions and conjunctions, but where the parentheses are just moved from one side to another, where we're so we can do that in this case, but these are not logically equivalent formulas. In the first case, I'm saying if it is true that S, then it is true that the relation if P then Q holds. In the second case, I'm saying if it is true that the relation if S then P holds, then it is true that Q. So logically, I'm expressing completely different things here. So exportation can only be used in the first case, where if I have S, then it is true that if P then Q, which means that if I have both S and P, S enables the relationship between P and Q, and P enables Q. So then I can say S and P, if S and P, therefore Q. But when the parentheses are arranged in this way, exportation doesn't work. Because first, the thing that I'm saying initially is that if this relation is true, then Q is true. It's a different kind of expression that I'm using there. So, yeah, basically trying to use exportation in the second case doesn't work. The parentheses have to be arranged in a certain way in order for exportation to be able to apply. All right, next. This one's should be real obvious. This is tautology. It sometimes will be useful, although you, at this point, might be unsure why that would be the case. But we'll get there. So tautology is if it's true that alpha, then it is true that alpha and alpha. And if it's true that alpha, then it's true that alpha or alpha. This sounds pretty redundant, and it is, but this is another example of logical equivalence. All right. So these are the rules, the main rules that we're going to be working with in the 3.2 or 3.1 and 3.2 homework assignments. We're only applying some of them, but going forward, we're going to be using all of them. Some rules more frequently than others, which will make others harder to remember. But it's important to practice these. And in the homework assignment videos where I work through these, I'll be working with the proofs and kind of talking through them. And a lot of what this course is, if you took it in the fall or the spring semester and we had more time, a lot of what we would be doing is just practice with these rules, doing proofs for this chapter. We're a little bit constrained on time, so we have plenty of time to introduce all the rules and everything, but we have less time to actually sit down and practice with them. So I encourage you to try to do that on your own, maybe above and beyond the homework assignments that I've given you. It's very important to be comfortable with these rules. You do have the benefit, I suppose, of students who took this class in person. You'd have to take your tests and everything in person, so you have to have all of these memorized. It's a good idea to have them memorized anyway, but obviously I can't control whether or not you look them up. But you're still going to have some facility in order to be able to use them for your derivations. So encourage you to practice these. If some of them don't make sense, feel free to reach out to me and maybe I'll try to explain them in a way that's more intuitive for you. Because it's important that you get kind of how these work and how you can get to one thing from another thing, etc. All right, so that's all for this section.